Hello guys, we're going to do a quick review of what we learned so far in AP Physics 2. So the first thing we need to review about is the Coulomb's law, which stated as force, electric force, is equal to K, which is a constant, times Q1, Q2, which is a charge of the particle 1 and particle 2, and divided by r squared, and times the unit vector. We don't really care about unit vector for now, so we just ignore it. And the attraction force is in the direction that is connecting the 2 points. And whether it is attraction or repel, it is determined by the sign of the 2 charged particles. If the 2 charged particles have the same sign, they will just repel, and if they have the opposite sign, they will attract. And for the value of k, we also can write k as another constant, which is 1 divided by 4 pi times epsilon. And you might think about why do charged particles attract each other. The reason is that the first charged particle will send out an electric field, and when the electric field reaches charged particle 2, they will just attract or repel. So how to visualize is that you can visualize the electric field as like water-like materials that is just expanding, and eventually it will reach the negative charge particle. And in this case, it will just attract, and the force is in the direction that is connecting these 2 charged particles. And you can also visualize it as a drop of water, and when it drops, it will just expand until it reaches this point, and when it reaches this point, it will just attract or repel. And moving on, we're going to review about electric field lines. So when lines are very close, the electric field at that point is really large, like this point. And when the lines are loose, it means that E is weak. That is the way we draw the electric field lines. And for the positive charge particle, the electric field line is coming out of it. So you can draw it as the diagram show in this case. And for negative charge particles, the electric field line is going into the negative charge particles. And for the case of plus and minus, and you can see it is just, this is going out, and this is go into the negative charge particle, and you just draw it like this. And some of the electric field lines will be very, very large, and just circulate at this point. So the final image will just look like this. Okay, moving on. We're going to take a look at Ampere's law, which is that the magnetic field is equal to mu times I divided by 2 pi r, where mu is a constant and I is a current of the wire, and r is the distance from the wire to the point. Whoops. So what I mean is that the distance r is this to this. And how is it derived? We might prove it at the end of the video. So if you want to watch it, just go ahead. And for the direction of the magnetic field, you can just use the right-hand rule, which is that if you have a sum, and this is in the direction of the current, and you just use your other 4 fingers and hold it around the wire. And let me clean up. And the direction of the fingers is the direction of the magnetic field. Okay, I'm not trying. Here's B. And moving on, and for this case, and we want to find out, oh my god, what is going on? And we want to find out the magnetic field at the center of the loop. So here's a formula given, which is mu I divided by 2r, and we might prove it at the end of the video. But in this case, you just need to remember this formula. And the third topic we're going to review about is that the magnetic field force or magnetic force felt by the wire is equal to I L cross B, and where I is a current, and R and L is the length of the wire, but there's a direction for the length, which is just in the direction of the current. Like for this case, like if you have a length of here, and here is a current going here. So the direction of L is in the direction of the current. And the magnetic field or magnetic force is I L cross B. And you can determine the magnetic field force using the right-hand rule. So like for this case, you have a current going in that direction, and B is going that direction. And we know that L cross B, as the magnitude of this, is just going to be ILB times sine theta, where theta is the angle between I and B, or L and B. And for the direction, it is L cross B. So you use this, the 4 fingers you have, and bend it to B. And you will see the sum is just going downward. And the sum is the direction of the magnetic field force. Okay? And for this case, this is just going to be, and if you have a vector A and here's a vector B, and the direction of the vector C is just, if you have 4 fingers and use your palm, the palm is pointing in this direction, in the direction of A, and your fingers will fold to the direction of the B. And you will see the direction of your thumb is just pointing upward. And the next equation is F is equal to Q V cross V. So what does that mean? Is that if you have a charged particle, example, if you have a positive charge ion which is moving in the V direction, the direction of the velocity, and if you have a magnetic field, and so the magnitude is equal to QVB times sine theta. And the direction you can see is in the right hand rule. And in this case, Q is positive, so, and V is in this direction, use your palm and fold it in that direction. And you can see the sum is going into the page. Wait a second. And and you can see 1 and 2 are just equivalent to each other, and we're going to show why. So for I, the definition of I is equal to Q divided by T. And for like in delta T or delta T time, the charge will move to this point to that point. So we're going to call it L. So I L B sine theta in this case is just going to be Q T and times L and B and sine theta. And if you move delta T to here, and you can see this is the charge. So it is going to be Q, and this term is just a velocity, QV and B sine theta. This is pretty cool actually, but you don't need to know this. And the next topic we're going to review is polarization. So polarization occurs when an electric field distorts the negative clouds of electrons around the positive atomic nuclei in a direction opposite the field. And this slight separation of charge makes one side of the atom somewhat positive and other side somewhat negative. So if you have positive ion and here are just negative like electrons, and if you have a field going that direction, so whoops, ignore that. So the negative charge will just go that way, and the positive charge will just move to that way. So we just distort like this. And in larger scale, it will just look like this. And here's the electric field. And for insulator like rubber, paper, and wood, like you can visualize polarization as a negative charge particle and a positive charge particle connected by a stick, okay, and like or a spring, okay. When the electric field is pointing downward, the positive charge particle will tend to move that direction, and the negative charge particle will tend to move that direction. And you can see the spring will be stretched, and this result is called polarization. And for conductors like metals, like the positive charged ions are not free to move because they are very, very heavy. But the negative charged electrons are free to move because they are very, very small compared to large charged metals. So when you apply electric field for, oh my god, if you apply E, those electrons are free to move, and the attraction between positive and negative is smaller than the insulators. So you will just move that way, and that way, and that way. They're free to move. And next, you can visualize it as electron C model. So it is like the charged negative electrons are like water. Like when you apply E field in that direction, the water will just flow that way, like freely. And next, like when there is no E, the particles will be just very, very random. And we apply E and there is a negative Q, it will be more organized. And the positive will tend to move to Q, negative Q, and the negative will tend to move away from Q. So this will result in, like, in larger scale, this side will have a lot of positive and this side will have a lot of negative. And for the case of semiconductors, like silicon and germanium, like when the temperature is low, it will behave like an insulator. And when the temperature is high, it will behave like conductors. So why is that the case? I'm going to explain why. So in low temperature, these negative and positive will just attract. And when the temperature is high, it will add energy to the bond. So the negative and positive will just, bond will just break. So they're free to move, just like the metals. The metals over here. And the next topic we're going to review is the structure of atoms. So in physics classroom, and for the first energy shell, the maximum number of electrons is 2e. So the maximum you can put is 2 electrons over here. And for the second shell, you can put 8 of it over here. And for the third, you can put 18s or 18 E's. And we're going to draw the structure of lithium. So if you first put Li over here, and lithium has 3 electrons, so it will just go to the first shell, and the second shell will have 1 electron. And for the boron, which is charged, and we just draw a structure of boron first. And you can see 3 of the electrons are removed, so we just erase this. And so the structure of B3 plus is just 1 electron and 2 electrons. And fun fact, we're going to talk about how color is produced. So if you have an electron at this point, and here is an energy, it will just give energy to this electron, and the electron will travel to outer shells. And fact is that the outer shells have higher energy, and after a while the electron will just go back and to lower shells. And when it goes back to lower shells, it will also release energy, and the energy is released in the form of like the light, because light has energy. So if it goes from n is equal to 3 to n is equal to 2, like you first find the energy of E3 and minus E2, and this is the energy of the light. And for different wavelengths, the light has different energies. So for a specific energy, we'll just produce specific wavelengths. So for like the case of like red, the wavelengths just quite long, and the energy is not very much. And for the case of violet, the wavelength is short, and the energy stored in the light is quite large. compared to the red light. And the third topic we're going to review is charging by induction. So, so if you have a negative charge particle over here, we will just attract or repel the negative charge electrons, and the electrons will just move away from the negative charge particle. And this will result in this side to become positive and this side to become negative. And when the negative side is connected to the ground, like also there's, and the negative are repelling each other. So when it is connected to the ground, the electrons are free to move away from this negative charge particle. So eventually, this will be all gone to the ground, and this will be resulted in only positive charge particles left in the metal, or the overall charge of the metal is positive. And so, when you just disconnect this part and remove the negative charge particles, the metal will be positive charged. And we're going to do electron affinity for this one. So which statement best explains why rubber rod become negative charged when rubbed with fur? So electron affinity means that the materials like to attract electrons. So in this case, you can see rubber likes electron more than fur. So that means rubbers is more wait, let me see. Okay. So the answer is C, I don't care. Okay, moving on. We're going to see how charges distribute in first metal and second in insulators. For the case of metal, we'll just evenly distribute on the outer surface of the metal. And when in equilibrium, there will be no charges inside the metal. Okay, there will be no charges. And for the case of insulator, because the charges are not free to move, so the distribution will be kind of random. And now we're going to take a look at this example. So we want to find out the angle theta, and this is positive charge with Q, and the mass is M. So the first force is mg, gravitational force. And the second is Fe, which is equal to kq squared divided by r. And here is tension. So by balancing out the force, we can see that the net force of the gravitational force and Fe must be the same direction as the tension, because in all direction the force balance each other out. So that means by vector addition, you have theta, and here is Fe is equal to kq squared divided by r squared, and this is mg. So what you have is that tangent theta is equal to kq squared r squared divided by mg. And for r, and the length of the string is L, so this is just going to be L sine, and r is equal to 2L sine. So plugging in, you can see sine theta divided by cosine theta is equal to kq squared mg times 4L squared times sine theta. And you move sine theta to that. To the left side, you can see sine cosine is equal to kq squared divided by 4 mgl squared. And by using cosine, is equal to 1 minus sine, and moving that to that direction, and you have kq squared divided by 4mgl squared is equal to 1 minus sine, and you just square it both sides, and you will eventually get sine. Okay, now we're just going to prove Ampere's law. So the first thing we're going to talk about is Biot-Savart law, so which stated that like for a small distance we just call dl and a direction of r, and this is the displacement vector, so you will produce a small force which is equal to mu divided by 4 pi I dl cross r divided by r squared, r cubed. So now for a long wire, and let me draw a diagram over here. Oh my god. And using the right hand rule, you can see the current is going up in this direction. You can see the dB is going into the page. For this point, it's also going into the page. You can see. So the dB will just add. It will just add. So you can take the integral. And now for a certain value of theta. And you can see that and we just label as y and this as x, and we can label this as 0.0y and this point as x 0. And so r is equal to x0 minus 0y, and this is equal to x y, and dl is equal to 0 dy. And now we have I dl cross r squared is equal to y d 0 dy 0 x y 0. Now you have x 0 plus y 0 plus z, which is negative y, or this one 0, and minus x dy. So ideal cross r is equal to I negative x dy. And plugging in, you can see dB is equal to mu 4 pi times I x dy r cubed, and r is equal to x squared plus y squared. And now this integral becomes mu 4 pi I x dy x squared plus y squared, and 3 over 2, and integrate from negative infinity to positive infinity, because we treat the wire as very, very long. And from this result, you can have this integral is just going to be equal to square divided by 2 pi x. And that is the result, which is consistent with the equation discussed above, which is this. And for the case of looped wire, you can see dB is equal to mu0 4 pi IDL cross R divided by R squared. And you can see this is going out to the page. This is going in that direction. And for one circle, like you integrate one circle, dl is equal to 2 pi r. So this will eventually come down to pi times 2 pi r times r divided by r cubed, which is equal to mu0 divided to I divided by r. And we're done.